So today's talk is regular expressions with Linux tools. I think most of you are familiar with the complex program by now. So I keep saying here that it's a new SCSE program. We're actually in our third year, but we cover non-programming skills needed to effectively use supercomputers. So some of the topics that you've seen in the past have been parallel computing concepts, Linux tools, bash scripting, security, batch computing, getting help, data management, and interactive computing. So a little bit of introduction. This really is one of my favorite topics. I find regular expressions to be kind of fun, and I hope that I convey to you how useful, how interesting, how powerful they are today. So they give you a way to identify a string that matches a specified pattern in a body of text. And they have their foundation in formal languages and theoretical computer science. And we're going to mention that very, very briefly. We're not going to dwell on it for too long. Now, the regex formalism, when you first see it, it could seem a little daunting, but they have very, very practical applications for computational and data scientists. So in practice, the implementation of regular expressions in computer languages, text editors, and Linux utilities, it goes well beyond the original definition. And this allows you to specify more complex patterns, back references, some other advanced features. And now, finally, while the syntax and the feature set for regexes can vary across languages, the basic concepts are universal. And in this tutorial, we're going to be focusing on their implementation in the Linux utilities, awk, sed, and grep, primarily in grep. But what you learn here, you could also incorporate into programming languages like Perl, Python, C++, R, and others. All right, so why do we need to understand regular expressions? So you can probably get by without using regular expressions, or regexes as we often call them. But if you do know how to use them, you can make your life much easier, especially when you combine these with other tools. So if you're a data scientist, you're probably going to spend much of your time performing really mundane, gritty tasks to get your data into a usable format. So I know a lot of folks, when they go into data science, they're thinking about the more exciting stuff, applying machine learning techniques to gain insights into the data and so on. But really, much of your time, much of your effort is going to be spent on getting data into the right format. So the data might not be set up quite the way you need. You might need to work with data coming from different sources. And if you use regexes along with these Linux tools, it's going to give you a way to pre-process that data, get into a format that's going to be ready to use. Now, if you're a computational scientist, say, focus mostly on doing simulations, I find that regexes are really helpful for extracting important information from the results of simulations, and also when preparing input files for high throughput computing workloads. So let's say, you often see this in computational chemistry and material sciences, where we need to run many calculations where the input files just vary slightly from run to run, and using a combination of tools like sed and regexes makes it really easy to set up those input files. Now, I'm going to say this is hopefully going to be a gentle introduction to regular expressions. Entire books have been written on the topic, and you can spend days, weeks, sometimes even months going really deep. I have a picture of the cover of the classic book on regular expressions, published by O'Reilly. And about 20 years ago, I had some free time, and I actually worked through this entire book. And it's exhausting, it's dense, it's probably deeper than any of you want to go. But what I'm going to try to do is distill what I think is really important about regular expressions for computational and data scientists who have other priorities. Many of you are probably maybe in graduate school and you're trying to finish your thesis, or you're a postdoc and you need to get your publications out. So you don't really want to spend a month diving into regular expressions. So instead, we're going to cover what I think are the essential basics that will satisfy most of what you're ever going to need to do with regexes. So prerequisites, I think you're going to get more out of this session if you're already familiar with the tools that use pattern matching, especially grep, but also awk and sed. And if these tools are not familiar to you, I recommend afterwards that you either attend the complex webinar, Linux Tools for Text Processing, go back, look at one of the recordings, or work through the materials that are posted online. So like all of our other presentations, you could find the PDF in this bit.ly location, bit.ly/complex, and the accompanying exercises and examples in this GitHub repo. All right, so we're going to dive into the regex formalism. We're not going to spend too much time on this, just want to show you, what the roots, what the foundation of regular expressions are. And this is a very computer science view of the world. The definition is a regular language is a formal language that can be defined by a regular expression. So really a very circular definition. And these regular languages have the following properties, and these are actually kind of important. So we're going to define an alphabet sigma. In your case, it's going to be the set of characters that we normally work with, letters, digits, punctuation, spaces. So the empty language is a regular language. This is actually important because we're often going to be doing matches that include empty strings. All of the elements of that alphabet are regular languages. If A is a regular language, A star is a regular language, and we're going to talk about what this star does in a few more slides. If A and B are regular languages, then the union and the concatenation are also regular. What this means is that we're going to be able to build up more complex regular expressions from simple ones. We could have compound expressions. And then finally, no other languages over sigma are regular. So I guess you could take that to mean that anything that could be expressed by a regular language, any pattern, is going to be comprehensively covered by these definitions. So let's look though at regular expressions in real life. So unless you do theoretical computer science or linguistics, you're not going to start with the regex formalism. Instead, you're going to work with what we call regular expression engines that provide an augmented syntax for constructing patterns and that are implemented in these tools and languages. So we're going to be going through all of these in this presentation. We're going to look at quantifiers. This is going to give us a way of describing how many of an element we want. We have a wildcard, which is a period. We have anchors that allow us to look for matches at the beginning or the end of strings. We can specify multiple characters and their negation using the square brackets. We have POSIX character classes that are predefined, specifying uppercase, lowercase letters, digits, spaces, punctuations, and so on. We use parentheses for grouping and vertical bar for alternation. Now, a few words about grep before we really dive in. So we're going to be starting with grep, which I think is the simplest Linux utility that does pattern matching. Now, grep is going to return all the lines from a file that match a given pattern, but it's often more instructive, though, to see what portion of the line resulted in the match. And to do this, we're going to configure grep to colorize the output. So if you're familiar with aliases, you could set alias grep equals grep -- color equals auto. And if you are using Expanse here at the San Diego Supercomputer Center, I believe that this alias has already been set up for you. Now, I know a few of you might be might be colorblind or limited in the set of colors that you can see. You might find it handy to set the color to something other than red if that helps. And then finally, throughout this presentation, the grep matches are going to be underlined to emphasize white space captured by the match. But this is not a feature of grep. This is just something that I added to the presentations. All right, so we're going to start off with the simplest regular expression, and that's just a literal string. So if you've used grep already, you've probably done this. Say you're looking to find all the lines in a document that contain a given word. So we're going to start off with a file, fruit.txt. All of these files, all of these examples are in the GitHub repo. And I know we're not going to have enough time to work through these in real time, but I'm going to suggest when we're all done that you go back, you download that repo, and that you do work through these examples. So let's say I wanted to do a search for all of the records that contain the string banana in all lowercase. So I could do a grep banana fruit.txt, and I get these two lines, and we can see that we have apple banana pear, cherry banana peach, and the matching string is highlighted in red. And again, I added the underlining to make it a little bit easier to visualize. In the next case, we do grep uppercase B, A-N-A-N-A. So this is going to match capitalized banana, but not lowercase banana. Okay, now we're going to start getting into some of the regex options. Now grep, it does have an option -I to make the match case insensitive. Sometimes this is what you want, but there might be unintended consequences. So regular expressions are going to give you a way to do this with a finer degree of control. So let's look at these two examples on the right. So if I do a grep-I banana, I'm going to get all of the banana in lowercase, banana in uppercase. But note that if this file also contained different capitalizations banana, say all uppercase, or just the first three letters, or just the ends, that we would get those also. But let's say that we only wanted the usual capitalizations banana, say all lowercase or starting with a capital B. We could use those square brackets to specify a class of characters. So here we have lowercase b, uppercase b in those brackets, followed by A-N-A-N-A, and now we pick up the lowercase banana, capitalized banana, but it would filter out all of those other possibilities that I mentioned in the previous example. Now, we're not limited to specifying just two characters, and we can also invert the match. We can use the caret within those square brackets to exclude the character set. So now we're going to look at another file, ash.txt. And this contains a series of words or a series of strings that all begin with a character and end with ASH. So bash, cash, dash, etc. And finally, the very last line is -ash. And I'm going to explain a few slides why I included that line. So let's say that we want to match all of the strings that begin with a B, D, R, or W, followed by ash. Here we can close those characters within the square brackets, and now we get bash, dash, rash, and wash. Now, let's say we want to match any character except a B, D, R, or W followed by ash. Here the syntax is going to be nearly the same, but now we're going to have a caret in front of those letters. So now we have within our square brackets, caret, B, D, R, W. So now we get cash, gash, hash, lash, mash, and finally -ash. Now, an easier way to specify a range of characters is by using the syntax x-y. So this is going to match all of the characters from the first one through the last one, and again using the usual alphabetical ordering. So let's say we wanted to match a D through an H followed by ash. Now in our square brackets we'd have D-H. We could also do an inverted match. So let's say we want to match any character except a C through an R followed by ash. Here we pick up bash, wash, and -ash. And then if we want to match a literal dash or a literal hyphen, we just make sure that it's the first or the last character so that it's not interpreted as part of the syntax for specifying a range of characters. So in this last example, within our square brackets, we have dash. So now we're matching a literal dash and then G-L, ash, and then finally ash.text. Now, don't worry if the pace seems a little fast for some of you. I know regular expressions, there's a lot to it. Think of this more as an introduction to all the features. And if anything seems a little too fast, maybe make a mental note and go back and work through these slides and work through all the examples in the GitHub repo. So, think of having homework after this presentation. All right, another way that we can match a choice of multiple characters is to use the POSIX character classes. So in these examples, we see that we're looking for lowercase letters or uppercase letters or alphabetical characters or digits or alphanumerics or punctuations, followed by OOT in the OOT.txt file. And, the results are what you expect. In the first case, we get, the lowercase b, the lowercase c, followed by oot. In the next example, uppercase F, uppercase H, followed by oot, and so on. I find that I don't use most of these POSIX character classes very often. I generally find it easier just to specify A-Z or 0 through 9 or combinations of these. But I do find, though, that the punctuation class is especially useful because I've written regular expressions in the past and I needed to, let's say I was looking for a punctuation that appeared at the end of a string. So I might manually enter, the period, comma, semicolon, and so on. But inevitably, you're going to miss something. And if you use the punctuation character class, you're going to pick up all of those punctuations. Now, just a word about the syntax. You might have noticed that the names of the POSIX character classes were enclosed by 2 pairs of square brackets instead of 1 pair. So for example, bracket, bracket, colon, lower, colon, bracket, bracket, instead of just using the single pair of brackets. Now this could be a little confusing because we're using the same symbol in 2 different ways. The inner pair of brackets are part of the character class name, while the outer are used by grep to define a set of matching characters. So hopefully the next 2 examples will make this point a little more clear. So on the left, I'm looking for a match of a lowercase letter or the digit 3 followed by OOT. So here I'm going to have my outer set of brackets, and then within there, I'm going to have the lowercase letter character class and the digit 3. And you see in the right, that actually included 2 different POSIX character classes, the punctuation class and the digit class. So, common point of confusion. Again, make sure that you have those 2 sets of square brackets, and keep in mind that one is part of the character class definition, the other is part of the regular expression syntax. And I just list the common POSIX character classes here. We've seen most of these. We also have character classes for spaces and tabs. That's the blank character class, and all white space characters. That includes new lines. And I find these to be really, really useful. And if you want to see the entire list, there's a link here on Wikibooks. So let me just see if there are any questions. Let me just check the chat. Okay, yeah, no questions yet. All right, so now we're going to move on to the next feature of regular expressions, and that's a single dot which matches any character except a new line. So you're going to start off, we're going to go back to our fruit.txt file. So let's do a grep B followed by 4 dots followed by A. So what this is going to look for is the letter B followed by any 4 characters followed by the letter A. And as we expect, we're going to pick up 2 instances of banana. Now in the next sample, we have a dot followed by an E, followed by 2 dots, followed by an H. And in this case, it's going to be any character followed by an E, followed by any 2 characters, followed by an H. And here we're going to pick up the 3 instances of peach. But it would have also, if we had in the file, say leech, we would have gotten that. And then finally, we have grep dot ea dot. So this is going to look for any character followed by ea followed by dot. And here we're going to match pair. We're also going to match the first 4 characters in peach. And notice in that last line, in the context of grep, that if we have multiple matches, we're going to get both of those. So we picked up pair and the first four characters of peach. All right, quantifiers. This is where I think regular expressions really start getting interesting. So everything that we've done up to this point involved matches of fixed length. Now quantifiers allow variable length matches and give you a lot more flexibility. This is where we really start getting into the full power of regexes. So we have a star quantifier, which means that we want 0 or more of the preceding element. We have the plus, which means 1 or more of the preceding. Question mark, which is 0 or 1. And then we could use this curly brace syntax to specify with a single integer exactly n copies of the previous element, an integer followed by a comma, which means at least that many, an integer preceded by a comma, which means at most that many, and finally a pair of integers to specify a range from nmin to nmax. So let's look at a few concrete examples. In the first column, I show the regular expression, and in the right column, the interpretation. So we're going to have the expression AB star C, and that's going to mean A followed by 0 or more B's, followed by a C. Next case, we have AB plus C, which means A followed by 1 or more B's, then a C. Next case, we use the question mark, which is going to indicate 0 or 1 B's. And then in curly braces, we have a 3, which is going to be exactly 3 B's. Next example, we have 3 comma in the curly braces, which means at least, or 3 or more B's. Next example, comma 3 in the curly braces, which means up to 3 B's. And then finally, 3 comma 5 in our curly braces, which means A followed by 3 or 4 or 5 B's, again followed by C. So again, kind of abstract, but we're going to see some examples where this is very helpful. So now let's look at a file, abc.txt, and this consists of lines with the string A followed by a variable number of B's, followed by a C. So we have AC through 5 B's. So if we do a grep AB star C, that's going to be A followed by any number of B's followed by a C. So it's going to match all of the lines in that file. If we use AB plus C, that means we're going to look for A followed by at least 1 B followed by a C. So that's going to pick up everything except the first line. If we do AB question mark C, that's A followed by 0 or 1 B's, so we get AC, ABC, and in the examples in the right hand of the slide, we search for 3 or more, up to 3, or 3 to 5 B's between our A and our C. All right, so you notice though, in addition to the quantifiers that I introduced some new syntax. You'll see that we have a capital E flag following grep, and we have the regular expression enclosed within single quotes. So the reason we did that is regular expression come in multiple flavors. There's the basic regular expression, extended regular expression, and Perl-compatible regular expressions. Now, by default, grep uses the basic flavor, which requires that the following characters be preceded by backslashes, our parentheses, our curly braces, the plus, the question mark, and the vertical bar that we're going to be using for alternation. So if we're using the basic regular expressions, for example, if we wanted to search for A followed by anywhere from 3 to 5 B's, I would have AB backslash curly brace 3 comma 5 backslash curly brace C. It works, but it's a little more awkward, a little bit harder to read, easier to make mistakes. The -E option tells grep to use the extended regular expressions, which don't need backslashes. And then finally, the single quotes are going to prevent the Linux shell from interpreting the special characters so they're passed to grep. So that, for example, a star is not interpreted as a Linux wildcard. Now, you really don't need the plus, the question mark, and this curly brace syntax. In fact, you could write all of the regular expressions just using the star quantifier, but life is going to be much easier if you use the full set of available quantifiers in your regexes. So I show here a table of regular expressions in the first column using the full set of quantifiers. And then in the second column, only using the star quantifier. So you could see, for example, in the second row, that we really don't need the plus. The plus, again, means one or more B's. We could have written that as B star. So that first B ensures that we have at least one B in our match. The B star is then going to be 0 or more. Now, I didn't really talk about alternation yet. I'm going to get to that shortly with the vertical bar. But in the next example, we have AB question mark C, which means A followed by 0 or 1 B's. And here we could write a regular expression, AC, vertical bar, ABC, which means to match AC or ABC. And then when we get into that curly brace notation for specifying a specific number or a range of counts, here, if we don't use the full range of quantifiers, if we're using just the star, we're going to need to start writing things out explicitly. So for example, AB, and then 3 in the curly braces, C, we need to write out that string explicitly. If we wanted 3 or more, we would need BBB, B star. And then as we start getting into the case where we need up to a certain amount or a range, now we need to start explicitly writing out all of the possibilities. So again, doable, but it gets a little ugly, a little tedious. And just a little bit of trivia, that star, it's actually called the Kleene star. It's named after the American mathematician Stephen Cole Kleene, and it is actually pronounced that way, Kleene. For many years I looked at this and I call it the clean star, but it really is Kleene. And if you know what a Kleene star is, your computer science friends will be impressed. But if you just call it a star or asterisk, everybody's gonna still know what you're talking about. All right, an important concept in regular expressions is what we call greediness. Now, by default, quantifiers are greedy, and they're going to find the longest possible match. So in the examples below, we're going to start scanning from the left until we find the first P, and then from the right until we find the first R. So it's really a little more complicated than that. We can go down this rabbit hole of backtracking and finite state engines. But if we only have one quantifier, you could think of that as a close enough working explanation. So now let's say we do a grep p dot star r, and this is going to mean p followed by any number of characters followed by an r. And we might think, hey, this is a good way to find matches like pair. But look at those first few lines. In the first line, we matched starting from that first P in apple through the R in pear. Same thing in the second line. In the third line, we matched from that first P in pear through the R in grape. And the last two lines, we just matched pear. So keep in mind, by default, quantifiers are greedy. They're going to look for the longest possible match. I'm going to just check the chat real quick. And okay, I don't see anything. All right. So let's move on to grouping. And again, I know we're covering a lot of material. Think of this, if it's going a little too fast, think of this as just sort of a first look at regular expressions, a glance at all the capabilities. And again, you can go back later, work through the exercises. So grouping. In our earlier discussion of quantifiers, recall that I mentioned that they apply to the preceding element rather than a single character. Now, regexes can group multiple characters together into a single element using parentheses. So we're going to look at the file, grp.txt, and all of the records in this file start with 3 zeros, end with 3 ones, and then we have a capital A and a capital B with variable numbers of the string XYZ in between. So 0, 1, 2, 3, or 4. So let's do a grep where we're looking for A followed by 0 or 1 instances of XYZ. And notice the way I wrote this expression. I have A and then in parentheses XYZ followed by the question mark followed by B. If I didn't have those parentheses, what I'd be looking for is A, X, Y, and then 0 or 1 Z's. So this gives me an easy way to group things together and to write these regular expressions without having to use long strings of alternation. So here we're going to pick up the strings with A followed by B, directed by B, and A followed by XYZB. In the next example, we're going to look at A followed by 2 or 3 instances of that string. So we get A and then 2 instances of XYZ or 3 instances of XYZ. So basically all of the quantifiers that we've seen earlier, they work exactly the same way here. They're going to apply to that string in the parentheses. Okay, anchors. Without any other specification, grep is going to look for a match anywhere in the line. Anchors allow us to restrict the match to the start or the end of the line. So start using a caret and end using the dollar. So let's go back to our fruit.txt example. And we're going to search for the string pair again. So we do grep pair fruit.txt. We pick up 2 lines where pair is at the end. To find a pair of strings in one line, type grep into it. We find two lines with pair at the end, 2 lines with pair at the beginning, and 1 with pair in the middle. Now, if we use the quantifier, not the quantifier, the anchor, caret, we use caret pair. Now we're only going to match pair when it occurs at the beginning of the line. And if we use pair dollar in that last example, we only match pair when it occurs at the end of the line. And let's talk about alternation. So we've seen a few examples of alternation already. Sometimes we want a single regex that matches 2 or more patterns. Let's look at an example, since we just introduced anchors, where a string appears at the start or the end of a line. And this can be done using alternation. So the first 2 examples we've seen already, caret pair for the start, pair dollar for the end. But if we do caret pair, vertical bar, pair dollar, now we're going to get matches where pair is either at the start or at the end of the string. And again, you've seen a few other examples of alternation along the way. Okay, I'm going to look at a little more complicated example. A really challenging task in writing regular expressions is to find matches that form whole words. Matching substring must be at the start or the end of the line, or preceded or followed by non-word characters, something other than letters, digits, or underscores. So this is going to come up a lot when you're processing text, where you're looking for that exact word, not part, but standing alone, not part of another word. So we're going to look at a slightly more simple example, something that seems like it should be pretty easy, and that is finding the lines that contain valid 5-digit zip codes. So we're going to try doing this first the hard way, and then we're going to see how we could do this the easy way with grep. So word boundary is the hard way. So let's look at the example text, zip.text, and this file is going to have lines containing valid and invalid zip codes. And to me, a valid zip code is going to be the string of 5 digits, separated by white space or punctuations, and not, say, with any extra characters or letters. So our file is going to start off with examples where we have some valid zip codes. 12345 is a valid zip code. Zip code 12345 is valid. This zip code 12345, comma, is valid. Valid zip code 12345, and then finally just the zip code by itself on a line. Now the next 4 lines all have invalid zip codes. For example, we have 123456. That's too long. A zip code should just be 5 characters. Next line has one that's too short. And then the next 2, I'm going to consider these invalid because we have extra characters tacked on there. A 12345 or 12345B. So this looks like it should be straightforward. We're just going to write our regular expression. It's going to be exactly 5 digits. So we have our 0 through 9 in the square brackets, meaning that we're looking for a digit, followed by 5 in curly braces. And we pick up all of the valid zip codes, those first 5 lines. We filter out the zip code that's too short, but you see we're going to have 2 that are incorrect. Sorry, 3 that are incorrect. We pick up the line, 123456 is too long. Here there's some ambiguity. You know, it's 6 characters. You could find a 5-digit zip code in there, but we don't know, is it 12345 or is it 23456? And the next 2 cases, we picked up the zip codes that had those extra characters. Now, if you were writing a letter and you use the zip code A12345, I don't know if that's going to get through or not. So what we really needed to do was write this big, ugly, regular expression with 4 different parts. And I won't go into all the details. You could work through this one on your own. But you see, we start off with the case, the 5 digits at the start of the line, followed by a punctuation or white space. Then the more complicated case, where the 5 digits appear in the middle of the line, preceded and followed by white space or punctuation. The 5 digits at the end of a line, preceded by white space or punctuation. And finally, a line consisting of exactly 5 digits. And when we do this, we see that we picked up all of the valid zip codes. But you'll notice also that we picked up some additional characters. So let's say that we were trying to extract the zip codes. And I'll show an example here where I use the -O option for grep so that we just get the matching string. You'll see that we've picked up the white space, the surrounding white space, and the punctuation. So in those second, third, and fourth examples, we get space 12345, space 12345, comma, and again space 12345. So there's really no easy way around this with grep, and we would have needed to pipe the output into another utility to remove those additional characters. But there's an easy way, fortunately, to define word boundaries. So we can delimit the match with backslash less than and backslash greater than. So that's going to denote the word boundaries. With grep, we could also use backslash b, and again backslash b at the start of the end to denote word boundaries. Or we could use the -w flag to select matches that form whole words. Now, all three of these are going to work with grep, but my preference is the first option since it will work with grep, awk, and sed. So the W flag is specific to grep, and backslash b has a special meaning in awk. Now, we mentioned greedy matching earlier, but I also want to mention lazy matching. So these regular expressions by default are greedy, meaning that they're always looking for the longest possible match. Lazy matching looks for the shortest match, and it's implemented in grep using the lazy quantifiers. Question mark, plus question mark, star question mark. So the quantifiers we've already seen, followed by a question mark. And we have to use the -P option for Perl-compatible regular expressions. So just comparing here, the standard default greedy matching on the left and the lazy matching on the right. So we can see when we do the lazy matching, if we do an A dot star question mark B, now we're going to look for the shortest possible matches. And in many cases, there's more than one match within the string. So we see in the first, second, and fourth lines that we've picked up A followed by 3 A's or 3 C's followed by a B. In the third line, we can see that we have a longer string, A, 3 lowercase a's, uppercase A, 3 lowercase c's, B. So in each case, these are the shortest possible matches. So something that you're not going to need to do very often, but just do be aware that grep has this possibility. Now you might be wondering, why Perl-compatible regular expressions? So Perl is a programming language that very few people use anymore. The typical Perl programmer is, I'm going to say, at least over the age of 50. You might find a few folks who are into Perl, but there are newer languages that are much more user-friendly, much easier to read and to write. But Perl, though, really set the bar for regular expressions. In fact, Perl was used very, very heavily for text processing, and it had this rich set of regular expressions that you didn't find in other languages or tools. So we are just about done with the features. I just want to mention escaping special characters. So like just about everything else in the Linux world, special characters can be escaped with backslash. And if you forget the backslashes, the errors can be very, very subtle. So let's look at this file, spc.txt. So this has strings of characters, but it also has math symbols, stars, pluses, we have question marks, we have parentheses in there. So let's say that we're looking for a string of 0 or more characters enclosed by parentheses, followed by an X, followed by, again, by 0 or more characters enclosed by the parentheses. Now, in that first example, if we just wrote out left paren dot star right paren X, left paren dot star paren, that's going to get one of the matches that we wanted, that MNO in parentheses X, PQR in parentheses, but notice that it also matched the string XYZ question mark. If we use those backslashes in front of the parentheses, now those are going to be treated as literal parentheses, and we're going to get the match that we expected. And in the next two examples, let's say we wanted a string of digits enclosed by curly braces. Here again, we need to use the backslash in front of those curly braces. Otherwise, in this case, we're not going to get the result that we expected. I think in that third example, the first first curly brace is interpreted as the start of the interval syntax, but then we don't have the expected digit. So I think that's going to break things. And then the last curly brace is treated as a literal curly brace. Now we've been talking mostly about grep, but I should mention that awk also uses regular expressions, but the default flavor is the extended regular expression. And the regex is also delimited by slashes. So here I'm really using awk just as a substitute for grep. You wouldn't normally use awk this way. I just wanted to illustrate the regular expression. Basically, all of the features that you had in grep regular expressions, you're also going to have an awk. But again, you don't need to specify extended flavor. You get that by default. And you're going to use those slashes to define the pattern. The sed is going to be very, very similar, except in this case, you need to again use the -E flag so that you get the extended regular expressions and don't have to escape the special characters. And like awk, we're going to delimit the regular expressions using forward slashes. Again, I'm not going to get into awk and sed here, but I just do want to mention again that everything that we've learned with grep is going to apply for sed and for awk. Okay, so it gets a little confusing keeping track of the flavors in the default. So I put together this table. Grep gives you basic, extended, and Perl-compatible regular expressions. And I show here in green the default behavior, which is the basic. Awk only gives you the extended regular expressions, and sed gives you basic and extended. And like grep, the default is going to be basic. Now, I do want to point out here with awk, if you're using awk on a typical Linux system, it's probably going to be a pointer to gawk, which also uses extended regular expressions by default, but you're generally going to be aware of this since awk is usually a symbolic link to gawk. And then one last thing about grep, this is not really a regular expression topic, but I think is a good place to introduce this. In user bin, you'll normally see one awk and one sed, and you're going to see a whole bunch of different greps. And if you ignore the symbolic links in the original grep, we are still left with a big list of different grep versions, BZ grep and E grep and F grep and so on. There's really just two of these that you're going to need. Grep with a -E is going to be extended regular expression, -F is going to be fixed pattern, and these replace everything that the deprecated E grep and F grep do. And I see I have a couple of comments here. Oh, just a question about the slides. Okay. So we don't need E grep, we don't need F grep. XZ grep searches for patterns in files compressed using compress, bzip2, gzip, and other tools. And this covers all the functionality of bz grep, ze grep, zf grep, and so on. And then ms, ggrep, and pgrep are mostly used by sysadmins. ptar grep and zip grep are used for searching tar and zip archives. So if we wanted to do a search for a pattern on compressed files, we could use xzgrep directly. And this is a feature that I just discovered a few years ago. I would always uncompress the file, and then I would do the search. But I, discovered xzgrep works just like grep. And one of the beautiful things about xzgrep is that you don't need to specify what the compression scheme was. It will figure it out from the suffix. So for example, if it ends with bz2, xzgrep knows that it's working with the file compressed using bzip and so on. And if you work through these examples, the fruit.txt, bz2, gz, xz, and .z, these are all the fruit.txt files just compressed using the different tools. So we are just about done. And I'm going to comment very briefly on large language models. So I think LLMs are great. I use them all the time in many different contexts. But if LLMs are so useful for writing regular expressions, why should I still study how to create them manually? I mean, you think, why should we be doing all this hard work? So first of all, I'm going to say the LLM might not do exactly what you want it to do. So I had asked ChatGPT, it said, write a said one-liner that replaces all instances of the string PEAR with 4x's, but only if it appears at the start or the end of the line. And ChatGPT gave me a very good, very useful said one-liner, but notice a subtle difference in the interpretation. I asked for the string PEAR, but ChatGPT assumed the word PEAR separated by spaces from other text. So this is going to be a little different. So if I had, for example, the word pairs, that would not, in that case, the PEAR would not have been substituted. So it's very subtle. Also, it only included, if I really want to do this on word boundaries, it didn't include punctuations. So again, this was a case where the LLM wrote a valid said one-liner for me with regular expressions, but not quite what I wanted. Second of all, sometimes it's just easier to write the regex yourself. So I asked ChatGPT to write a grep one-liner that outputs all lines in the file that contain the pattern A, followed by exactly 2 or 3 occurrences of the string XYZ, followed by B. And it gave me the grep one-liner. This is perfect. This is exactly what I needed. But in this case, I felt that it was more work to try to formulate that in words, rather than to just write the syntax directly. Also, I feel that I'm more likely to state my request incorrectly in words than in regex syntax. And this is something that happens all the time, let's say when we're trying to define math expressions. When we say it with words, we don't necessarily capture the parentheses correctly. So finally, I asked ChatGPT to answer the question on the previous slide. Namely, since LLMs are so useful, why should I still study how to create regexes manually? And I'm not going to go through everything here, but there was a really good answer. Includes understanding the basics. You'll be able to customize the solution. And then finally, I think this is important, critical thinking. Writing the regex manually forces you to think critically about the problem that you're solving. Encourages you to break down the problem into smaller logical steps, which can enhance your problem-solving skills in general. So with that, I'm going to wrap up. Few conclusions. When you combine regexes with tools such as awk, sed, and grep, they give you really powerful ways to search and manipulate text. I mentioned this a few times as we run along. Don't be overwhelmed by all of the regex options. Learn what you need to get started, then pick up the rest incrementally along the way. If you really want to learn this, I'm going to say go back, work through all of those examples in the GitHub repo. We just mentioned this. Be careful when using LLMs to help you construct regexes. They're not 100% reliable, and sometimes it's just hard to specify in words exactly what you want the LLM to do. And then finally, many programming languages, R, Python, Perl, and C++ have regexes. Now the syntax is going to be a little different sometimes than what you see here, but the concept that you learned are all going to be universal. And with that, I am all done. I am happy to take any questions.